Okay, so this video is about diffraction and its effect on the images formed by telescopes. So, first of all, we need to understand what diffraction is. We're going to go back to the wavefront picture of waves that we used when we were first talking about refraction and show you some waves coming through a gap. So the red object there is just a barrier, and what you can see is the wave progressing through the gap, and this is what we'd expect if we didn't have diffraction. That the wave is absorbed at the barrier or possibly reflected back, and that all we get on the other side is the wave where the gap is just continues on. So we get this kind of sharp shadow zone region behind the barriers. But that's not what actually happens, okay, in most cases. What actually happens is the wave will spread out once it goes through the gap, and that's what diffraction is, okay? Waves spreading out after passing through a gap. The yellow dotted line here is just showing you kind of the angle of the spread. There's actually quite a complicated pattern of intensity of the waves in this spread, but all you need to know about is sort of how much spread there is, depending on two things. So, we're now going to look at what affects the amount of diffraction. And the critical thing really is the wavelength of the wave, which remember is the distance between the two wavefronts there, compared to the width of the gap. And the idea is that we only really get diffraction, right, when the wavelength is sort of similar in size to the width of the gap. If we have a gap that's much larger than the wavelength, then we won't really get very much diffraction at all. So let's have a look at how that works in practice. We've got the original situation up in the top right for reference, and the first thing we're going to look at is what happens if we double the size of the gap. So we've kept the wavelength the same here, and what happens is there's much less diffraction, okay? There's much less spreading. We've gone through a much smaller angle of spread there, okay? So with a wider gap, the angle of the spreading has decreased. Okay, the second situation now, what I've done is I've increased the wavelength, I've doubled it, so you can see the distance between the wavefronts is now double what it was before, and we've gone back to the original gap size. So again, we're comparing this to our original situation. And what happens in this case is we get much more diffraction, we're much more spreading because the wavelength is now large compared to the gap size. Okay, so with a longer wavelength, the angle of the spreading has increased. So the critical things to remember then from those two situations we've seen is that if you have a smaller gap or a larger wavelength, then you will get more diffraction. Okay, so smaller gap and or a larger wavelength will increase the amount of spreading of the light going through that gap. So how does this all relate to telescopes? Well, what actually happens is when the light goes into a telescope, you are only looking at some of it. You have effectively formed a gap, which is what happens when the light passes through what we call the aperture of your telescope. The aperture is just the opening at the front of the telescope. And that's likely to be very similar in size to your objective lens or your objective mirror if you're using a reflecting telescope. So that means that all telescopes will suffer from diffraction to a greater or lesser extent. And what we said previously was that what matters is really the size of the gap, so the size of the objective, compared to the wavelength. So we need to just recap some stuff from P2 about the EM spectrum, and we're just going to look at the parts of the spectrum. So you remember the radio part of the spectrum has a very long wavelength in them. So it's a wide range, but a typical radio wavelength might be even as long as 100 meters. Okay. And then we've got microwave, where we're talking a few centimeters. Infrared, 10 micrometers, so that's 10 millionths of a meter. And the visible part of the spectrum, 500 nanometers roughly, 500 billionths of a meter. And then ultraviolet X-ray and gamma ray with such short wavelengths that we're not really going to be worried about diffraction occurring for them. So remember what we said was the bigger the wavelength, the worse the diffraction gets for a given gap size. So diffraction is much more of a problem as you head to the left of this spectrum, so down the radio and microwave end. So, for example, this picture here is of the Very Large Array, which is a radio telescope in New Mexico. All radio telescopes have large dishes to try and reduce this diffraction effect, because the dish basically forms an aperture. The radio waves go into the aperture, and you get diffraction. You can't avoid it. And in fact, you can see what the VLA does there is it uses several radio dishes to kind of cheat to make the total area seem a bit bigger. You can link those dishes together and the effect of diffraction can be reduced. They're actually building a telescope called the Square Kilometre Array, which is going to span across 2 countries with several sites to try and get an even better radio telescope, which is suffering even less from diffraction, and for other reasons they want to have this massive thing. But basically, if you want to have a radio telescope that doesn't suffer too much from diffraction, you need to make it really big. It is important to realise, though, that even though diffraction might not be an issue for visible or infrared telescopes very much, you would still want to have a large collecting area in order to be able to look at distant or faint objects. So distant objects because the light from them will have spread out a lot by the time it gets to you, or faint objects just don't give out very much light at all. That's not to say there's no diffraction in infrared and visible telescopes, it's just very, very, very small, and other things like the problems with the lenses or the mirrors are likely to be the limiting factor on the quality of the image in a telescope like that. Okay, so last thing just to look at is kind of what does it actually look like? So we've got an imaginary image here with 4 stars in it. So the telescope is looking at 4 stars shown in the green rectangle here. Got a large white one, a smaller yellow one, which is only got a small angular separation from it, a bright red one in the foreground here, and a very, very dim star in the distance, so it might be very low temperature. Okay, and on the right hand side here we have just a representation of the size of the telescope aperture. So this isn't anything compared to the size of these star images. This is just going to show us how the aperture of the telescope is changing. So if we were to shrink the aperture of the telescope, what would the effect be on the image? Well, what happens is if we shrink the aperture, we're making the gap smaller. That means the light spreads more, which basically means the images get blurred out. Okay, so you can see that what's happened is the very faint star light has been spread out even more, and these 2 stars here, the images from these 2 stars are starting to blend together. If we shrink the aperture even further, then we have an even greater effect. Okay, so the 2 major effects we've seen is the spreading out of the images due to diffraction. In the real thing, it won't be just simple circles, there'll be slightly more complicated spreading, but it gives you the general idea. And also, what happens, which we didn't discuss before, is basically if you make the gap smaller, you're collecting less light. If you make the aperture smaller, and that means the whole image gets dimmer, as you can see, that's happened as well. So this causes a couple of problems. If you've got 2 objects that are only slightly separated in angle to start with, it might be impossible to what we call resolve them. So you won't actually be able to tell that you've got 2 objects there. If you're trying to take an image, say, of a binary star system, which is 2 stars orbiting around each other at the centre, then that might be a problem for you, because they won't be separated by very much an angle. Depending on how far away they are, it might be a very tiny angle. It might be impossible to resolve those 2. Okay, and the other problem we've got, we can see that this very dim object starts to become undetectable. I mean, we can just about still see it on the video, but if you imagine that's got to be detected by a CCD camera or a piece of film, eventually the detector won't be sensitive enough to register the presence of that star, and so it'll be like it's not even there. So that's the reason that we want to have these large apertures, to connect enough light to be able to image the faint objects and distant objects, and to stop diffraction from limiting what we call the resolution, our ability to resolve 2 different stars as being separate from each other rather than just one big blob of light. Okay, so that's diffraction and its effects on telescopes. Hopefully that's been useful for helping to understand the reasons that we need large apertures.